air pressure, it requires a little bit more thought about, because if you are sort of standing somewhere, you aren't just having a load of air particles. They don't just sit on top of you like some kind of weird headgear, as I'm trying to draw in this way. What they're actually doing is constantly in motion, and you are getting walloped all the time by little particles that are going to smack into you and leave. That is something that gives air pressure. Okay, so the idea about, in a gas, the particles are moving with, and it's really important, these key words, with rapid random motion. And that means that what there is inside this is there is a distribution of directions. So I could put one here and it's going off in that direction. It's just we're not really interested in it because this one is not going to hit you because it's going that way. But some of them might be going really super fast, and some of them might be going really super slow, and some of them might be going that way, and some going this way, and some going off in this direction. So all these little particles are going and swimming around in these rapidly in different directions, and they're moving pretty fast. Okay? Now, why you get a pressure on you is that as these things move around, eventually they're going to hit you, and what you feel is the combined overall impact of all of them striking you. And in doing so, there will be a collision. And haha, what have we just seen? In collisions, there is a force because of momentum and fun like that. And so what will happen is these things will smash around and will generate that pressure by lieu of those collisions. Okay, and there's a fancy way of saying when there is a sort of discussion in terms of like how they generate pressure. So when they collide with a surface, they will exert a force on it. Okay, so you get a force. I'll put that in. Ooh, yeah, that thing is important enough to say force. So, and the pressure from the force exerted by all of the particles over the area of the object. Okay, so this kind of has a weird cancelling effect, a bit like with the water pressure, is that if you take a bigger object, so if you take a small object, well, it's not very big, so there won't be that many sort of collisions with it every single second. But it's got a small area, so you divide it. If you take a bigger object, there'll be loads more collisions. But what they're doing is they're all striking it over the course of an entire size of the object. So you end up with essentially them cancelling out. The size is immaterial, because the bigger you are, the more collisions there can be, but then you're dividing your pressure, so you cancel them out. And it's why thinking about the pressure is something that's more useful than just thinking about the force. Because the force, if you have a bigger object, it will experience a bigger force, but that doesn't mean anything in terms of what that means for things. So if we wanted to think about fundamentally what is going to affect the air pressure somewhere, so the air pressure that is experienced is going to depend on factors such as the let's say the density of the gas. So that kind of is a measurement of how much there is and what kind of area is it, what kind of volume is it condensed within, and its temperature. And what I'm going to do is we're going to see over the course of the next few lessons, we're going to actually see how we can deal with that. What rules that we can apply that link sort of the various aspects of gas pressure to things like changing the temperature and so on and so forth, or if we have a fixed amount of gas and we put it into more or less volumes. So yeah, we're going to look at those things. But first, what we're going to see is some demonstrations. Oh, and I can't write that word. So there we're going to see some demonstrations, which will be in the next video. So yeah, smiley face.